Hello, class. So in the previous video, we started on section 2.1, right? So this section, which I'm calling just the integrating factor. And we went over this method, and the idea was, given a first order linear ODE, the method for finding a solution was find this function, which we're going to call the integrating factor, such that when you multiply both sides of the differential equation by this function, you get this very nice property that the left-hand side becomes a derivative. Once we have the left-hand side of a differential equation as a derivative, it's very easy to solve for y explicitly as a function of x. Right? So that was the process. Okay? So now let me just write this as a theorem. So, let me not, I don't want to use light blue, let's just use black. Okay. So given a first order linear, so remember this only works for linear ODEs. So given a first order linear differential equation, and of course we know what this looks like. This looks like dy dx plus some function p times y equals some function g. So given a first order differential equation, right, suppose, right, so I mentioned that the only assumption we're going to need is that p is continuous, right, because we're going to have to integrate p in this method. So suppose p is continuous on some interval I. Right? And again, in terms of this interval, you always want to take the largest one. So suppose p is continuous on some interval I. And for continuity, it doesn't have to be open. Right? So usually for why do you need open intervals? Anytime you're working with derivatives, you do need open intervals because derivatives are not defined on closed intervals. For continuity, the interval can be open, can be closed, it doesn't matter. Right? So I'm just going to write some interval I. So given that you have a first order linear ODE, suppose that p is continuous on some interval I. Then mu equal to e to the integral of p dx is an integrating factor on I. Okay. Once we know what an integrating factor is, well, we know how to solve for y. It's pretty straightforward. Okay. So this is the main theorem, and this is basically the only thing that's going to be new in this section. Right? We already went through all the work, because really the hard thing was finding what the integrating factor is. Once we know what it is, well, now we can actually go and solve differential equations. Okay? So let's go through an example. So example 1. And again, I'm relabeling my ordering of examples, all those numberings every time I'm starting a new section. So example 1, solve the differential equation dy dx minus 3y equals 0. Okay. So the method is pretty easy. Again, all we want to do is find mu. Well, the only thing we need is really find what p is and check on what intervals is p continuous and choose the largest one. Okay? So in our case, our p is -3. Remember, p is whatever's in front of y. Right? So for our purposes, p is -3 and p is continuous everywhere. Right? Because it's a constant. Right? So for us, this implies that whatever integrating factor we find is going to work over all real numbers. Right? So our domain is usually the real numbers. Okay? So it implies we can find our integrating factor, which is going to be e to the integral of p dx, which for our purposes is e to the integral of -3 dx. Again, we integrate, so integral of -3 is -3x, so we get e to -3x plus a constant. Now, as I mentioned before, we're only interested in one such function mu. We don't need infinitely many. We only need one of them. So as I mentioned, when we're finding mu, in that case, the constant in front, we just let it equal to 1. So in this case, we can just let the constant here be the simplest constant we can find. Well, what's the simplest thing you can add to something? Well, that's 0, because that doesn't change anything, right? So, and this is the process you always want to do. Find mu, whatever constant of integration you find, just set it equal to 0, because again, we don't need infinitely many functions mu, just one. So we can let mu be the function e to the negative 3x. And again, this works on the whole real number line because p is continuous everywhere. Once we found mu, then it's very easy to find general solution. Why? Because remember what we did was multiply both sides of the differential equation by mu. And so multiply both sides by mu, we get, let me just write what mu is. We get e to the negative 3x times dy dx minus 3y equals negative e to the negative 3x times 0. Now we know that by construction, this left-hand side is exactly the derivative of mu times y. Right, so this left-hand side is just the derivative of mu, which is negative 3x times y. Now, you don't actually have to check this because by construction, mu is constructed such that it satisfies this. So that this is always true. If you want to check whether you found your function mu correctly, you can write out this derivative using the product rule and actually make sure that it equals this thing here. But again, if you're comfortable and you're sure that you did the work correctly, you integrated p correctly, then you're fine. You don't actually have to do that. Okay? So again, by construction, the left-hand side we know is equal to this. The right-hand side, well, it's 0, right? Any function times 0 is 0. Okay? We want to get rid of the derivative, so we integrate both sides with respect to x. So we get e to the negative 3x times y equals a constant. Right? You integrate 0 with respect to x, and you get a constant. Right? Divide both sides by x, solve for y, so divide both sides by e to the negative 3x. You get that y equals a constant times e to the 3x. That looks kind of weird. And that is your general solution. As simple as that. And again, this is a solution on I, on the interval you found to begin with. Right? Because remember, all this process works assuming that we can integrate p. So this process is kind of restricted to the interval that we choose on which we can integrate p. So in this case, this is on I equals all real numbers. As simple as that. So a very easy method. It's also a reason why I didn't mind covering it later. It's such a simple thing to do that I thought, well, I just cover it when we start talking about methods for linear ODEs. In the book, you notice how they do it, further in the back, so earlier, but I think this is a good place to do it. So let's actually try another example. Let's see if I can find something that's a little bit more complicated. Oh, good. I found a good one. So example 2. Actually, let me write it. It's purple. It's fine, I guess. So solve the differential equation x dy dx minus 4y equals x to the 6 times e to the x. Now, I think, so this example, it's still going to be short. It's not going to be a lot of work. How much time have I actually spent? So I did this. Yeah, I think we can do it in one video. But just for sake of not keeping the videos as short as possible, this is a very natural place to stop. So I'm basically just going to do this example in the next video. If you want, before I go over this in the next video, so before you watch it, you can try to solve this yourself. Try to find the solution, try to find on what interval does that solution work.